All right, guys, this is Unit 5, and this is the last piece of the unit on stoichiometry, which is a funny word to say, but basically stoichiometry is a fancy way of saying chemistry, math, okay? So we're going to use what we know of balanced equations, we're going to use what we know of predicting products, and we're going to try to now add a mathematical piece into that. And we're going to say, okay, not just what products we're going to make, but how much of that product can we make, and so on and so on. So we're getting back to that concept of like recipes, you know? So I'm going to give you a reaction, and we're going to use that as our example moving forward, and we're going to walk through the steps of how to do this. So we're going to go back to our super simple fuel cell reaction. Which is this. So what do you think we should do first? And I'm going to call this step number 1. And I hope you are saying balance the equation. That is the most important thing we can do here. And you're going to see why very, very, very shortly. But, okay, balancing the equation is huge. So we go 2 and 2. Okay. So when I say you want to think about this as baking, that's what we got to think about. So I'm going to ask you a question, okay? And then we're going to walk through the steps of how to do that using this reaction as the example, okay? So I'm just going to rewrite this down here just for ease of use here. So I'm leaving out the states of matter for right now, so hopefully that's okay. So here's my question to you, okay? If we start with 10.0 grams of each reactant, how much water can we make? All right, so think about that for a second. If we start with 10 grams of each reactant, right? So that would be like we're starting with 10.0 grams of this one, 10.0 grams of this one, and I'm actually even going to say, I'm going to add something here. I'm just going to say in grams. So we want to know how much of this can we make in grams. Now, you might be thinking, well, this is easy. Law of conservation of mass. If I start with 20 grams of stuff, I need to end up with 20 grams of stuff, right? And you would be correct. The problem is that 20 grams of stuff all water? Or is it some combination of water and leftover ingredients from the reactants? And the answer to that is, well, we don't know. And we got to figure that out, okay? So if we go back to kind of thinking about baking, right? And you go back to, like, let's say you want to go make some chocolate chip cookies in your house, right? And you're thinking to yourself, I'm starving. Like, what's the maximum amount of chocolate chip cookies I can make with what's in my pantry right now? So you go to the pantry and you get all the ingredients. You get the sugar and the flour and the butter, all this stuff, right? Chocolate chips, okay? And you bring it all back to the table. And you're like, how many chocolate chips can I make? Right? How many batches of cookies can I make? And you have all the flour and sugar in the world. And you only have one bag of chocolate chips. Okay? Well, the answer is you can only make one batch of cookies because you're going to run out of chocolate chips. And even though you have tons of the other stuff, you're not going to really use that because if you're actually following the recipe, you're going to end up with excess of something, right? You're not going to perfectly have everything matched up in your pantry. And it's the same thing here with chemicals, right? So if I just randomly say, all right, let's just grab 10 grams of each thing, let's mix it up and figure out how much product we can make, I'm not going to be able to use all of that. One of those is going to run out first. And I got to figure out which one, and then I got to subtract that out and figure out exactly how much of just water I'm going to make, because that's the goal here, okay? And so there's a step-by-step process on how to do this, okay? So we said step 1 was balance the equation. Step 2 is going to be to convert into moles. Okay? So the reason we do this, right now we're in grams. We're starting with 10 grams of each thing. We need to be in unit of moles because that's going to allow us then to use the balanced equation, which has ratios here. So for example, right now we have 2 to 1 to 2 in terms of a ratio of substances in this reaction, right? I need a 2 to 1 ratio of hydrogen to oxygen. And that's in terms of molecules, not mass, right? I don't need double the mass of hydrogen. I need double the amount of atoms of hydrogen, and so on. So by converting this into moles, I can then use the ratio that I created in the balanced equation, okay? So that's the first thing we're going to do is convert to moles. Once we're in moles, okay, then we can use the balanced equation to convert from moles of reactants into moles of product. Okay? So this is basically a big dimensional analysis problem. Right now, we're starting with grams of hydrogen, grams of oxygen. I want to talk about water. So I'm going to convert them to moles first. Then I'm going to actually convert them into moles of water. And the final step is going to be to convert out of moles and into the desired unit. Okay? So let's walk through this and set this up as a dimensional analysis and see what this looks like. Okay? So I'm starting with 10 grams of H2 and 10 grams of O2. And my first step after balancing, right, is going to be here. Convert into moles. If you learn nothing from me this entire year, please understand that you will never go wrong in your chemistry life if the first thing you always do is convert to moles. All right? So remember that. When in doubt, convert to moles because then you're going to be able to do a lot of other stuff. Okay? So even if you see a problem on a test and you're like, I have absolutely no idea what to do, convert to moles and you will get partial credit, I promise you. Okay? So we're going to do that. 1 mole of H2 is, so a hydrogen weighs 1.01, so this is going to be 2.02 grams of H2. So that is going to be our step 2. Okay? So let's do the same thing down here with oxygen. 1 mole of O2 is going to be oxygen weighs 16, so it's going to be 32 grams of O2. All right, so that's the first thing. Then we got to move on. Step 3. Use the balanced equation to convert from moles of the reactants into moles of the product. So I want to cancel moles of hydrogen. And we're trying to figure out water. So I'm going to do that. I'm going to do the same thing down here. Moles of water, moles of O2. And what I'm going to do is I'm going to go to the balanced equation, okay? So this is our step 3. And I'm going to literally just write down the relationship between the two substances I'm talking about. So for the first one, I'm talking about hydrogen and water. What's my relationship? Here we go. 2 hydrogens to 2 waters. All right? 2 to 2, or 1 to 1. Okay? I'm just writing down the coefficients from the balanced equation. That's it. Let's go to the second one. Now we're talking about water to oxygen. Okay. 2 waters, 1 oxygen. That's my recipe. Write it down. Exactly like the balance equation says. Now, again, this is glorified unit conversion here. We're not doing anything crazy. We're just doing dimensional analysis to get what we want. Step 4, convert out of moles, right? This is step 4. Into the desired unit. Well, our desired unit was grams of water, right? That's what the question was asking. We are right now in moles of water, so let's cancel that out. What is the relationship between grams and moles of water? That is always true. I'm going to go to the periodic table and say that 1 mole of water is 18.02 when you add it all up. Okay? And now I'm done. I am in my desired unit, which is grams of water. All right? So let's do the math. Let's get some numbers and then figure out which one to use. So I'm going to say 10 grams of hydrogen divided by 2.02 times 2 over 2, or 1 over 1, times 18. That's going to give me 89.2 grams of water. All right, next one. 10 grams divided by 32 times 2 times 18.02. This one gives me 11.3 grams of water. Very different numbers. Okay? So we'll call this scenario A. Okay, scenario A. I'm going to get an answer of 89.2. But in scenario B, I'm getting an answer of 11.3. So which is the answer? Okay? Well, the question then is, what does this math mean? Right? So when we do this math out, what we're saying is hypothetical. Hypothetically speaking, if this reaction works perfectly, and I use every atom of every compound, what is my possibility? Okay? So the way we've set this up, we've run this through for each of the 2 reactants. We don't know which reactant's going to run out first. This goes back to our recipe thing, right? Making the chocolate chip cookies. You go to the pantry, you get all the stuff. You got to figure out which reactant is going to run out first, and then that is your driving force to get your answer. So what my math is showing me here is, right, hypothetically, sorry, it was kind of a crazy circle there. There we go. Okay. Hypothetically, if I start with just 10 grams of hydrogen and plenty of everything else, right, like no worries about anything else, and I use every drop of that 10 grams of hydrogen, my maximum possibility of water is going to be 89.2. Okay? Assuming no limitations. Now, I'm going to run through that same thing here. Okay? Same thing here. What if I start with 10 grams of oxygen, independent of everything else, right? Assuming I have plenty of everything else, what is my maximum possibility of product? Well, 11.3. Okay? So how do we figure this out? So what's the answer, right? What is the answer? Okay? The smallest amount of product is the answer. Okay? The smallest amount of product after doing this is the answer. So in this case, our answer is going to be 11.3 grams of water. That is the maximum amount of water I can make under these circumstances. Even though, right, I'm looking up here, even though I calculated 89 grams up here, that was assuming I used all 10 grams of hydrogen, which clearly we didn't, right? Clearly we ran out of oxygen first, okay? And so what we do is we would say that oxygen is the limiting reactant. Oxygen is the limiting reactant. In other words, it is the reactant that is going to run out first, okay? So it's going to run out first. In other words, it's going to determine what our product is. So this is actually not feasible given these conditions, okay? Because if I start with 10 grams of hydrogen, I'm going to need a whole heck of a lot more of oxygen in order to make this work. Now, we could figure that out mathematically if we want to, and we'll get into that in the next couple weeks. But I'm going to kind of run through this and be like, nope, not possible. It's got to be this one, okay? So whenever you're given multiple amounts of multiple reactants, you got to say which one's going to run out first. And the easiest way to do this is simply just to run through the math for both of them and pick the smaller number and say, yeah, that's got to be it, okay? And so what we call this is, right, 11.3 grams of H2O is the theoretical yield of this reaction. Theoretical meaning, perfect world laboratory setting, okay? So what does this mean? Well, this means that if I threw 10 grams of hydrogen and 10 grams of oxygen in a jar and mixed it up, I would get 11.3 grams of water and then leftover hydrogen, right? Leftover hydrogen gas, because there's excess. So we would call oxygen the limiting reagent, okay? But we would call hydrogen the excess reactant, okay? Hydrogen is the excess reactant. We have more than enough, right? More than enough, okay? So 11.3 would be like the maximum yield possible of water, pending everything goes perfectly. So the last thing I'll say here, and you can even call this, if you want to call this step 5, I guess you can, right? Step number 5 would be percent yield. So what if you produce 10.6 grams of water in the lab? What is the percent yield? Right? So you're like, all right, I go and I do this and I actually get 10.6 grams. What does that mean? Okay. Well, percent yield is very simple. And it equals actual amount over theoretical. Okay? So actual meaning from a lab, theoretical meaning from the math. Times 100%. So what's our percent yield here? Okay, well, percent yield equals actual from a laboratory setting, in this case 10.6 grams, over the theoretical, which is the math, which is our 11.3 that we predicted we would get, times 100%. And that means 10.6 divided by 11.3 times 100% is going to be 93.8% yield. which is pretty good. So again, what does that mean? That means we were 94-ish% effective or efficient, okay? Why is it not 100? Well, that's where you got to come up with laboratory error, right? So, for example, these are all gases, right? Like maybe the container wasn't perfectly sealed and some gas particles escaped. Maybe you didn't stir it very well, right? So not every atom had a chance to react. Maybe you spilled some when you were mixing, right? And some was lost that way, okay? So for the most part, right, you're never going to actually get 100% yield. It's a mathematical prediction, okay? So this is the idea. This is chemistry math, right? You're going to start with a certain amount of reactants, okay? We don't know which one's going to run out first. So what we're going to do is pretend, right? We're going to pretend like each one, right, is individual. So I'm going to say, all right, what if I had 10 grams of hydrogen and plenty of everything else? How much am I going to get, right? Independent of the oxygen. Then I'm going to do the same thing for oxygen. What if I start with 10 grams of oxygen, independent of everything else, and figure out how much water I'm going to make from that one? So we walk through both of those with the math, and we say, which one's going to run out first? Well, in this case, the hydrogen, because that gave me this kind of way blown up number. And I'm going to focus on the oxygen, okay? So that's how we do this. Stoichiometry, chemistry math. There are a lot more tricks to the trade we will learn as we get going, but that just gives you a rough sense of how to do this, okay? We're going to do this as a lab activity next week, and hopefully that made sense. Bring your questions to class, and we will go over whatever you need to, okay?